Hi everyone. In this lesson we will discuss the HJM Framework, which was introduced by Heath, Jarrell and Morton in 1992. This is a way of modeling the term structure by specifying stochastic differential equations for the instantaneous forward rate corresponding to every maturity. We therefore have infinitely many SDEs, one for every maturity, though we model these using only finitely many sources of noise, i.e. we use a finite dimensional Brownian motion to drive these SDEs. In that case, no arbitrage considerations will impose conditions between the drift and the volatility of the instantaneous forward rates, as we shall see. These are called the HJM drift conditions. It then turns out that in a risk-neutral setting, in order to obtain an HJM model, all you need to do is to specify a volatility structure for the instantaneous forward rates. Up to now, we have studied interest rate models in which the short rate is the only explanatory variable. This approach has the following distinct advantages. Firstly, if we specify the short rate R as the solution of an SDE, then this will allow us to use Markov theory, which leads to partial differential equations, for example via no arbitrage, or the Feynman-Katz theorem, or the so-called Kolmogorov forward and backward equations. In that case, we can often obtain analytical formulas for bond and bond option prices, and this is very helpful for calibration, as analytical formulas will allow one to calibrate a model much faster than otherwise. But the short rate modeling approach also has the following distinct disadvantages. Firstly, it is unreasonable to regard the short rate as the only explanatory variable. It is difficult, for example, to incorporate views about different times in the future if one uses one variable to model the entire yield curve, which, as I've mentioned before, has instruments stretching out 30 years or more. It can be quite difficult also to fit a realistic volatility structure. And in order for the model to have even a remote chance of being correct for pricing and hedging purposes, it is necessary to invert the yield curve, i.e. to calibrate the models, which can be difficult. For models such as Vasicek or CIR, actually calibrating the model exactly to the yield curve is impossible. For models such as Ho-Lee and Hall-White, which can be calibrated exactly, the calibration is a non-trivial exercise. Multi-factor models overcome some of these disadvantages, but at the cost of reduced intuition. The economic meaning of the underlying factors may be quite opaque. The Heath-Jarrell-Morton or HJM approach circumvents some of these difficulties by specifying dynamics for the entire uncountable family of instantaneous forward rates. For each maturity capital T, it assumes that the forward rate, FTT, has real-world dynamics given as follows. Thus we have a stochastic differential equation here for every capital T, and each of these SDEs has its own drift process alpha and its own matrix-valid volatility process sigma. We also have an initial condition, which is that the initial forward rate is the actual observed forward rate that we glean from the market. Here W is a finite dimensional Brownian motion under the real-world measure P, and as I already mentioned, alpha and sigma are stochastic processes which we assume are adapted and sufficiently regular, for example bounded and jointly measurable in the little t and capital T variables, to allow us to perform the operations that we will in the future. The advantages of this approach are the following. Firstly, the initial term structure is fitted automatically because it's an initial condition. So there is no need to calibrate this model to the initial term structure of bond prices, although you will still have to calibrate to volatilities for option pricing. Secondly, it is easy to incorporate views about different maturities, because we have many different SDEs, one for every maturity capital T. Of course, there are disadvantages also. The main disadvantage being that we have so many stochastic differential equations. But as we have only finitely many sources of noise, this turns out to be not completely unmanageable. However, given a drift alpha and a volatility sigma and an initial term structure of instantaneous forward rate F star, we can solve the SDEs for the forward rate, which gives us the entire term structure at all times for all maturities, and thus the entire term structure of bond prices. Recall that the bond prices and the instantaneous forward rates are related as follows. Since we have only finitely many sources of noise and infinitely many traded assets, there is the possibility of arbitrage in the bond market unless the bond prices are interrelated in a specific way, i.e. all zero coupon bonds must have the same market price of risk. This will impose conditions on the functions alpha and sigma, as we shall see. Notice that HJM is not a model, but a framework of models for the bond market, just as short rate models form a framework for modeling the bond market. Now we can easily let the stochastic processes alpha and sigma depend on past history. Hence, in contrast to short rate diffusion models, HJM models need not be Markov. We'll have a bit more to say about Markovianity of HJM models towards the end of this lesson. Earlier, in the lesson on Introduction to Term Structure Modeling, we derived the following relationships between the dynamics of bond prices, instantaneous forward rates, and the short rate. I'd particularly like to draw your attention to C here, which relates the dynamics of the instantaneous forward rates with the bond prices. In other words, it specifies how to go from instantaneous forward rate dynamics to bond price dynamics. Let's now derive the HJM drift conditions. We will assume that the bond market is arbitrage-free in the following strong sense. There is a risk-neutral measure for bonds of all maturities. We will then show that there is a multidimensional stochastic process lambda, which is independent of the maturity capital T, and which is such that for all maturities capital T, we have the following relationship between the drift alpha of the HJM model and the volatilities. Here is the proof. From the previous slide, we can obtain the bond price dynamics from the instantaneous forward rate dynamics as follows. Here capital A is given by the negative of the integral of alpha, which means that if we take the derivative of capital A with respect to the maturity variable, we get minus alpha. And similarly, the bond volatility S is given by the negative of the integral of the instantaneous forward rate volatility, which means that the partial derivative of S with respect to the maturity variable is equal to minus sigma. Now suppose that we use a Kirsanov transformation with kernel minus lambda to change to a new measure Q. In that case, the new dynamics of P are given as follows. As you can see, we've added the volatility of the bond times the Kirsanov kernel to the drift, but we've left the volatility unchanged. And here WQ is a Q-Brownian motion. Now, in order for this Kirsanov transformation to construct a risk-neutral measure, it is necessary that each bond has drift equal to the short rate. In other words, it is therefore required that this expression here is zero. It is then easy to see that lambda is just the market price of risk of the zero coupon bonds for every maturity T. In other words, all bonds have the same market price of risk. Now, if we take this expression over here and we differentiate it with respect to the maturity variable, capital T, we obtain the following. We will also use the fact that the norm square of the volatility vector of the bond price is given by the product of S with its own transpose. Rearranging this equation yields the result. So in order to specify an HJM model completely, assuming that it's driven by D sources of noise, we need to specify a volatility structure, in other words, a volatility vector which is d-dimensional for every maturity capital T, as well as a d-dimensional stochastic process lambda, which plays the role of the market price of risk. With these two inputs, we can then determine alpha completely. Now, if we specify alpha and sigma beforehand, we can try and solve for lambda. We then have uncountably many equations in just d unknowns, namely the unknowns lambda 1 up to lambda d, one equation for each capital T. And because we have more equations than we have unknowns, this system is typically overdetermined. In other words, we cannot specify alpha and sigma arbitrarily. Instead, we proceed as follows. We specify the volatility surface, sigma. We choose D benchmark maturities, T1 up to TD, corresponding to very liquidly traded bonds, for example, and specify the drifts for those maturities. We then solve the system star above of D equations now for the D unknowns, lambda 1 up to lambda D. Then all the other alphas for maturities which are not benchmark maturities will now be given by the equation star. This is if we try to model directly under the real-world measure. However, it's often convenient to bypass this and model the instantaneous forward rate dynamics directly under the risk-neutral measure, as we shall do now. I.e., as for short rate models, it may be convenient to bypass the estimation of the market price of risk and to model directly under the risk-neutral measure Q. In that case, we have the following stochastic differential equations, where now W is a Q Brownian motion. Since under the risk-neutral measure the market price of risk is 0, the risk-neutral HJM drift conditions reduce to the following equation. And thus, in the risk-neutral world, the drifts alpha are completely determined by the volatility surface sigma. There is no need to estimate it. So, to create an HJM model, we therefore just need to follow the following steps. We must estimate or otherwise specify a volatility surface sigma. More about that just now. We can then calculate the drifts alpha using the HJM drift conditions. We also observe the term structure of forward rates at the initial time, which will involve building a yield curve for all maturities. We can then integrate the STE for each of the instantaneous forward rates to obtain the following. And once we have that, we can compute bond prices and the prices of other interest rate derivatives. A little bit more about the volatility surface sigma. Typically, we assume a parametric form for sigma. In other words, sigma involves a number of parameters that need to be estimated. For each possible set of parameters, we can then follow this procedure here to determine the prices of, say, caps, floors, and swaptions. And then we can use an optimization routine to determine the parameters which best fit the caps or swaptions prices. In other words, we have to calibrate the volatility surface to interest rate derivatives. We can't use bond prices for that because those are fitted automatically as an initial condition. In the next video, we'll have a look at some examples of HJM models.